Okay, we'll go ahead and take a look at the calendar. We just had our last class, and I'll give them back later on this period. Today we have our last day of new material. We'll talk about power and exponential regression. We've seen that word regression a bunch of times this semester. It's more of the same, just allowing ourselves some new functions when we use the calculator. This TBA and the last day of classes, Monday, will just be review days for us. So after today, we're done with new material. We'll spend Friday and Monday just reviewing for the final exam, which is happening Wednesday. 1 week from today, this course will be done. Starting time is 1 o'clock, although I think we'll probably make it 12:30 or something like that. More on that later. So I know that many of us are tired and just really ready for summer to get here and to get some sleep. With whatever energy you can find hidden somewhere inside of yourselves, there's a week left in this course. This is the time to find those hidden reserves of energy and just make a last push. We've got no other grades to come other than the final exam, but the final exam is worth a full 20% of your grade. That's an opportunity for people who haven't had the best grades this semester. It's an opportunity. 20% is worth a lot. You can really push your grade up with a good performance on that final. On the other side of the coin, 20% is a lot, and if you have a bad performance, it can really take a good semester's worth of tests and quizzes and push them down. So I think everybody kind of has something here at stake with it worth 20%. So I know we're tired. I know some of us are sick or have just gotten over colds or something. Find that energy. One last push here. 1 week from now, we'll be all done. Okay, on page 80, we'll start up here with number 1. Can we go to Michael? Okay, Brian, number 2. Okay, so let's pause right there. All right, so I wrote this question, I don't know, like back in the summer or something. And what just happened on Saturday of this past weekend? The Kentucky Derby, right? The first race in the Triple Crown. The Kentucky Derby happened. Horse racing is big, big business. Turns out that the average number of horses that a racehorse, average number of races that a racehorse has entered is a lot different today than it was 50 years ago. Do you think that racehorses, are entering more races today than they were 50 years ago, or less races today than 50 years ago, and why? So, Michael, why? Okay, so stronger animal rights. Maybe we have like regulations, limitations to how many races a horse can enter. Eric? Same idea with the animal rights. Iris?
Horse racing is also becoming a bit less popular.
Okay, so what does that mean to you about the number of starts for a horse race? Fewer races, so fewer starts. Okay, other thoughts? Okay, Katrina, number 3. Okay, so what has happened over the last 50 years to the number of races a horse enters? It's gone down. It's gone down pretty significantly. Used to be about 11 races was a career for a horse. Now we're talking at about only 6. Why is it? Because horse racing is big business, and putting a horse out to stud might be a lot more lucrative than actually racing them and maybe winning some prize money from winning a horse race. Taking breeding, yeah. So like racehorses are like built to be racehorses. It's not just like random baby horses, and then if they happen to be fast, we'll recruit them for the races. They are bred to be fast by taking horses that were really fast and mating them. If we did this as people, what do you think? Yeah.
Our legs would get longer, stronger, we get faster.
Like, could you imagine? I mean, like, could you imagine the question? Like, if somebody was just like, hey, we should breed people that are really fast. Like, I mean, we just, like, we wouldn't do that, right? Like, we would look at that and be like, that's so unethical. There's no way we could do that. But it's exactly what we do with horses. We do exactly that with horses. Do we take smart people and breed them together? Do we take pretty people and breed them? Well, it's Hollywood,
Well,
but
they usually do that themselves.
yeah. But there's like this ethical line that we cross without even batting an eye for the horses. That there's no way we would do this with humans. But in any event, this is what it is. So how about we do some regression? So I'm gonna type this data in. It's nothing new. You don't need to follow along. There's a big group activity where you're going to type in plenty of data on your calculators today. So let me just type this stuff in. I'm going to type in the data first. So what do you think? Which one is the X and which one is the Y? I've got number of races and the year. Which one do you think is X?
X is the year.
Yeah, like if time is in the process, then it's X, right? I'm going to go ahead and do years since 1900. So that'll be 60 for that one. So if I'm doing years since 1900, then how much is 2010? Is 110. Okay, so we'll do 110 there. And then the next one is what? 90, and then finally 60, and then we'll go over, and then 6.1, 7.9, and 11.3. Okay, Zoom. You guys remember the best one, right? Zoom stat. What happened? I didn't turn the plot on. It'll find it if I turn it on. Okay, so let's make sure we turn it on. Up there, plot 1, you can see it's not highlighted. Hit enter. Now it is highlighted. Now, if I do zoom and then stat, now it knows to find the dots. The dots are finally there. Okay, there we go. On the bottom axis, time is passing. On the vertical axis, horses are racing in fewer and fewer races. And that's what we see. What kind of a thing do you think is a pretty good fit for those 3 points? Looks real close to linear to me, so let's go ahead and ask for the best fit. We've done this before. All the directions are written in the packet on the next page that you can see here, number 4. And then what do I tell it? And then to put it in to Y1. So we'll go to vars and then ask it to put it in to Y1. Okay, R is negative 0.998. Good fit or bad fit? That is a very tight fit, right? Very close to -1. Are you surprised that it was -1 instead of +1? It's decreasing. We knew that if the line was going downhill, then it would be a negative thing. So that looks pretty good. So then we can maybe predict in 2050, if that trend continues, I can use it to maybe predict how many horses I keep saying that, how many races a horse will compete in. I guess what I'm interested in is plugging a number in to Y. What number corresponds to 2050? 150. Yes? So we're just plugging 150 in for X. And by that point, racehorses, if this trend continues, will be racing in about 2 races a year. What if I were to keep going? Maybe 250 years? Races will be negative. Okay. So the model breaks down at some point, right? This is the danger in trying to use the model past the time that we've already had. I'd be a lot more comfortable using this model to predict maybe what was happening in the 2000s, in the 90s, in the 80s, in the 70s, than I am predicting, 30 years from now, 100 years from now. At some point, that model is not going to be accurate. So, you take all the predictions with a grain of salt. Okay, so we've seen linear stuff before. Let's look at an example of one that looks different from all the things we've seen before. Can we go to Tyler for number 4? Sure. Okay, so I don't know if you guys have felt this in your lifetime, but in my lifetime, I can remember a time when people just did not wear their seatbelts. It wasn't cool, it was annoying, it was perfectly fine, like as a little kid to sit on your dad's lap while he was driving the car. And like now, there's like you got to be in a car seat until you're like 23 years old or something. So like there, I have witnessed a change, and I can remember back when in a time when wearing your seatbelt was not a given. But now you get into somebody's car, it's just automatic, right? And there were a lot of things that happened over the last 30, 40 years that changed our society's view of seatbelt usage from being, whatever. I'm a safe driver. You don't need to wear it. To, well, you got to wear it. It's you got to wear it. Just everybody wears it. It's the law. So what I'd like to do is I'd like to plot the data here, because I can see that definitely seatbelt usage is going up. It was 11%, then it was 21 and 49 and 61, and then over 80. But was it a straight line thing? Like as time passed, was it just a straight line increase, or is it something different? And like I just want to see the dots. So let's take a look at the dots. Again, you don't need to graph these. I will tell you the new part that we're doing, but you can just watch this part. You have to go into y equals and turn that plot 1 on. Okay, so let's type in some data. Again, which one do you think is x? Do you think the percentages or the years? All right, so x is going to be years. All right, so let's see. It says Congress set safety standards in the mid-60s, but 15 years later, we were at 11%. So mid-60s, let's say 65. 15 years later, 80. Okay, so the first data point is 80, and that's going to be an 11. Okay, what's the next data point here? I keep going down. It says seatbelt usage rose to 21% by the mid-80s. 85. And at that moment, it was 21. Next one, 1990 was 49%. Next one says 61% by the mid-90s. What happened here? That should be 49. Okay, by the mid-90s, so we'll say like 95-ish, and over here it should be what? 61, and then finally today, 2009, that's when the book came out. What do I put? 109, make sure we're consistent there. And then over 80. 82, great. Not an exact science. Okay, first thing I'm gonna do is get that thing out of there. We're going to do zoom and then stat, and it will find the dots for us, and we will see something increasing, but maybe increasing in a way that we've never seen before. We have not drawn or looked at any graphs that look anything like this thing. And so if you kind of imagine like trying to connect the dots in some smooth way, okay, what would you say about the way that things are increasing in the beginning? Slow or fast? It's pretty slow in the beginning. But then between here and here, you can see there's a big jump. So I would say that's increasing pretty fast in there. And then what about here? Then it's kind of slow again. Like it's just not as steep out there as it is in here, right? So it was like increasing a little bit at a time back in the early 80s. Then we've got all of those things that Tyler read for us about, like society accepting and maybe more traffic, more policing, the lights and the beeps if you don't wear your seatbelt. All that stuff happens, and while that stuff is happening, you see this big jump. Okay, why did it slow down? If everybody's using seatbelts, why doesn't that just keep jumping up and up and up? Everyone's already wearing them, right? We don't have a lot more to gain. Like if we're already at 80-something%, then there's not that many people left to gain. So it can't get above 100%. It's got to level off someplace. Okay, so what is that? Well, it's not a line. It's not a parabola. It's not any polynomial, because polynomials don't level off. Polynomials either end up going up or down, or some combination of these two things, right? They don't level off like this. Okay, so here's a new kind of thing. If you go to this page, the next page, there's a whole bunch of pictures. And depending on what the picture looks like, I've made some suggestions here for what kind of regression you should use. All right, so start with the beginning. What kind of regression do you think if the points all look like they line up on a line? Linear regression. If it looks like that, quadratic regression. If it looks like this guy with 2 turning points, remember that probably means it's a degree 3, cubic. If it's got 1, 2, 3 turning points, probably a quartic, degree 4. Okay, turns out the calculator, TI-83, doesn't go any higher than quartic. You can look in the list. Quartic is the highest degree for a polynomial. Then we had new things. Last time we talked about power functions. Something like x squared is a power function. Something like x to the 2.1 is a power function. Something like x to the 0.3 is a power function. And there's a couple of different kind of varieties. This guy right here looks an awful lot like a square root function, which is a power function. This one over here, well, I mean, it doesn't look too far from say this piece. But what's the difference? Yeah, it's going to go through the origin. Maybe that one doesn't, maybe the top one doesn't go through the origin, but maybe there's just no picture on the left. You remember a lot of the graphs? Yeah, a lot of the graphs we looked at last time, there was no picture on the left-hand side. So if it just magically starts and then looks like a parabola, perhaps it's a power, as opposed to being a full-on parabola which has both pieces. Okay, exponential things, we have seen those. There's an exponential growth. There's an exponential decay. Here's a problem. This looks quite similar to that. Yes? So if you just show me some dots, I'm going to have a hard time deciding whether it's the one or the other. They look quite similar to me. Now, it turns out there's some tools that you might talk about in a pre-calculus class, if you guys continue on, that will allow you to maybe look at the data. Like actually, if you had the numbers in front of you, you could do some stuff with the data to maybe decide which one is more appropriate. Without those tools at this moment, what are we going to do? We're going to do both on the calculator. The calculator will tell us which one is better by telling us that r-squared number. Okay, and then logarithmic, we've seen graphs that kind of look like that. Logs kind of grow slowly and slowly and slowly. And then the new one, logistic. So this will be the only day that we talk about logistic stuff. They look like that. What have we seen recently that looks like that?
Population growth.
Yeah, maybe population growth. The seatbelts look like that. Out of all the ones I showed you, seatbelts look like that. So what we're going to do is try a logistic growth. So turn that one on. We'll quit out of here, and we go stat, and then to the right. And then here, this is the list that matches up exactly with the list that I gave you in the packet. And the very last one here says logistic. So we hit enter on logistic. I'm going to want to see the graph, so I'm going to ask it to graph bars to the right, function y1. Okay, now I just want to pause for 1 second. Everybody watch, we'll hit enter, and we're just going to watch it calculate the logistic. What do you notice? It takes, I don't know if you remember, but the linear one was like that. Okay, that's a far more complicated equation than any other ones we've asked it to find. There's a whole bunch of gobbledygook up there. Turns out that the equation of a logistic is of the form constant over 1 plus another constant e to the negative constant x. Crazy equation. We're not going to use it, but if you wanted to write it down, those are the numbers. I just want to see it. How's it look? Looks pretty good. They do. You want to talk a little bit about that? Mm-hmm. Yeah, so like we're imagining time passing here, and then maybe the, can you pause for 1 second? Just pause for 1 second. So we got time passing over here, and then on the vertical, we've got maybe the number of cases, number of people that have this disease. And in the beginning, not many people have it, so they aren't really like transporting it to other people. But then we get to kind of this critical part in the graph where there's like a lot of people getting a lot of other people sick. And then why are we, and then people have had it. Like if anybody's going to catch it, has pretty much caught it. It's the same thing with the seatbelt usage. Yeah, so epidemics look exactly like that. Good. One other thing, what did it not tell you? R-squared. I just don't think the calculator calculates R-squared. I don't know that there is an R-squared for a logistic. I think all the other ones you'll see an R-squared, but this one you just have to look at it and say, okay, I think that's good enough, or I don't think that's a good fit. Okay, any questions on that? So then what you're going to do, you can skip past the directions if you know how to do all this stuff. If you need a refresher, talk to the people at your table or go look at the directions that we just skipped past. But on 84, there are 6 regression examples. So what you are going to do at your table is you're going to type all the data in. I'd like everybody to type data in. I have extra calculators in my office. I'll grab some in a minute. You're going to type the data in. You're going to write down an equation and the value of r squared. But you got to make a good choice in there somewhere. Is it a line? Is it parabola? Is it a cubic? Is it logistic? Make a choice. If it's not clear to you, try several. Pick the r squared that's the best one. Derek. Yeah, so logistic, the only thing we can appeal to when we think it's logistic is just the straight question, do you think that looks good? For that data, I would say it looks good. If you had a bunch of data that was in a line, I would say that doesn't look like a good curve. So that's the only thing we can do for logistic. Okay, who needs a calculator? 1, 2, all right, we'll go get some and work with each other. Probably there's somebody at every table that needs a little push, a little reminder for how to do the calculator stuff.